remember that always when we were talking about the simplex method and LPs and all those things, and when we were talking about these tableaus, I said you cannot make up a tableau just by putting the numbers in there. Because everything inside a tableau is representing the solution. If you do it outside the tableau, you're doing a matrix operation over and over and over and over again. Instead of those matrices, we put them inside a tableau, which is a better way of representing those, a shorter way of representing them, and so on. And I said, you cannot make up a tableau. Every element of this tableau has some sort of relationship with the other elements. We are going to be looking at the tableau and its structure. How is a tableau structured for any iteration, not just for the first or the last, for any iteration? The point is, given a specific basic variable set, a basis, given a basis, can you write the tableau at whatever iteration it is? It may be the 6th iteration of a big problem. The moment that I say, this is your basis, can you write the tableau elements? Can you fill out the tableau? I can say, is this solution optimal? Is the solution of x1, x5, and s2 optimal? Of course, your answer is, how the heck I know? And we would say, create the tableau, see if it ends up to be optimal or not. To do that, we need to go back to the structure of the problem, the LP, and we always work with the original LP. Incidentally, that's how computers solve. They don't create tableaus. What they do is that they keep a record of bases. And every time that they need to create something, they will create them. Tableau is a nice representation, but there's too much repetitive information in a tableau that doesn't need to be there. All those 0, 1, 0, 0, 0, 0, 1, 1, 1. Everybody knows the basic variables are identity matrix. So some people do a short tableau. They drop the identity matrix information from the tableau and only put the non-basic variables information. But still, the computers do not keep track of all these stops. Rather, they keep track of the basis. They say, this is the basis. And for computer, it doesn't make any difference. It will take a millisecond to do the calculation for large matrices and so on. So you say, this is the basis. It creates everything that you want for you, instead of creating and putting it inside the memory. So what computers keep is the original problem. So let's take an LP. We will do the standard maximization. Four variables, 3 constraints, all of them in the form of less than or equal, maximization. This is an example that we are doing. To put it into a standard form, we have to add S1, S2, and S3 here, with S1, S2, S3 greater than or equal to 0. In matrix format, this problem is maximize z equal cx subject to ax less than or equal b with x greater than or equal to 0. And you remember, these are all matrices and vectors. So when we say x greater than or equal to 0, what that means in matrix format. That's x, and that greater than or equal to 0 means this is greater than or equal to that's what it means. This is a matrix notation. A is what? Negative 1, 4, 0. 1, 1, 3, 2, 1, 4, 1, 3, 0. That's what A is. That's what A is. So that's your X, that's what your A is. What is the C? C is a row vector. Is 3, 5, negative 1, and 2. What is the S? S is a matrix. The matrix of the coefficients is 1, 0, 0, 0, 1, 0, 0, 0, 1. You need to be very comfortable with these things, because everything in here depends on your good understanding of those. When I say C, I say original values, not in a standard form, nothing else. Original values. So C is 3, 5, negative 1, and 2. A is whatever you see in here. What is the B vector? Is a column vector, 10, 20, 15. Okay? B is going to be 10, 20, and 15. C is going to be 3, 5, negative 1, and 2. And A is going to be negative 1, 4, 0, 1, 1, 3, and 2, and 1, and 4, and 1, and 3, and 0. What is the first tableau that we make if I want to set up the Simplex Tableau? It would be S1, S2, S3. Okay, 4, 0, same. A, 1, 1, 3, X1, X2. That's negative 3, that is negative 5. X3 is going to be positive 1, 2, 1, 4, 2, 1, 4, X4, 1, negative 2, 1, 3, and 0, S1, S2, S3, and the right-hand side will be 10, 20, and 15. With that 0 and 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. That's usually the first one that we do. And that's a basic feasible solution. Why? Because all of them are positive, and essentially because all of these are less than or equal 0, which means 0, 0, 0 is always less than these numbers, so origin is a basic feasible solution, and that represents the origin, because S1 that much, S2 that much, S3 that much says X1, X2, X3, X4 are non-basic, thus 0, and that represents the origin. So starting from that point on, you say, okay, well, this is okay. That I don't need any special feature. But what if this one was X1, X4, and S3? Which means maybe 2 iteration or 3 iteration down the road. How would I write that? We know the structure. We know the Tableau structure. We can write that Tableau in 5 minutes. How? By memorizing a little simple format. What that format is this. This represents the initial basic feasible solution. Initial basic feasible solution. What was the initial basic feasible solution right here? S1, S2, S3. Where was this? That was the location. In here, you would have the rest of them. These are what you are going to be memorizing. This location is always a matrix. That location is always a matrix called B inverse. That is the most important location that you find, because everything else depends on this B inverse. This location is B inverse times B. This location is B inverse times A. That location is CB, B inverse. These are all matrix products. This location is CB, B inverse A minus C. And in here, you would have the XB, set of basic variables that you are introducing. So let's start. Out of X1 through X4 and S1 through S3, you choose 3 of them. Okay, so we'll go with XB, the set of basic variable. She says X2, X4. You can, S1 did you say, or S1? I want to investigate that basic variable set. That's where that B is. And I say, okay, now that you know what XB is, you need to find the actual B. Actual B is the coefficient of these basic variables in the original problem. x2. So that is x2, that is x4, and that is s1. I'm looking at the coefficient of these three. What are the coefficient of x2? 1, 1, 3. 1, 1, 3. What are the coefficient of x4? 1, 3, 0. What are the coefficient of s1? 1, 0, 0. Okay. So appropriately makes sense that if I have xb and b, I also have a cb. What is the cb? Is the coefficient of these basic variables in the objective function, original objective function. That was the c, just written from the original objective function. So for x2 is 5, for x4 is 2, and for s1 is 0. The rest just fits into this. You can start building here. You can start building your tableau. What would you do? Where do you start? B inverse. I have B. I calculate B inverse. Of course, you can do them by hand. But you can be smart and say, oh, Maple. You go to Maple, you look at that, and it says, this is how you find the inverse of a matrix. It's a little command. You put them in there, you introduce your matrix, you define your matrix, and you say, calculate the inverse. It calculates the inverse for you. Whatever number you get, you put in here. Then you multiply what you have gotten into A. Whatever you get, you fill this side of the tableau. Multiply it by B, the little b that is representing the right-hand side. You place it here. Multiply it by CB, place it here. The same in here, and you do have your complete table. Now when you do this, two things might happen. After you finish this, you might notice that problem has the optimality conditions satisfied, which means all these numbers are greater than or equal to 0. You would immediately say, this problem is optimal, that solution is the optimal solution. That is the optimality condition. Because I did not start from the first tableau, calculate the mean ratio What does mean ratio do? Guarantees that the next solution is feasible. Guarantees that the next solution is feasible. You're just throwing out a solution. So although this may be satisfied, you still need to look in here, because B inverse B may end up to be negative. And if it is negative, has optimality conditions satisfied, but not the feasibility. So, structure of a tableau has this format. This need to be memorized. That's the only thing that you need to memorize in this class, plus some dual stuff. The rest is practice. It is very simple, very, very simple. So let's do another one, and we will write the complete thing such that everybody is comfortable with. We are going to change that from this to another one. From that to another one. And of course, who would like to share with me their selections?
I had a question, like if the b inverse times little b is like negative, you just gotta select another solution.
No. You just say this solution is infeasible. This is whatever we had in here is what? It is a extreme point, but it may be an infeasible extreme point. Okay, we don't know until we do the calculation. So, someone else share with me 3 selections there.
x1,
x1,
x3,
x3,
s3.
and s3. Okay, I'm going to do it like this, s3 and x3, to get a different flavor. Who can tell me what CB is?
CB is -3.
Is -3. Don't do -3.
0 and
0 and
3, 0 and 1.
is 3, 0 and -1. Now that's CB. Who can tell me what B is?
-1, 4, 0.
Minus down.
Yeah.
-1, 4, 0.
0, 0, 1.
0, 0, 1.
And 2, 1, 4.
And 2, 1, 4. B inverse will be -1, 4, 0, 0, 0, 1, 2, 1, 4. That will be calculated. Okay? CB, B inverse will be, we don't have these numbers, so we are going to make up something for them. And so CBB inverse will be equal to 3, 0, minus 1 times what do you think the result of this multiplication will be? Is it going to be a matrix, a column vector, a row vector? Remember that thing that you were supposed to memorize? How did it look? It looked like it's going to be a row vector. How many elements do you think it would have? It would have 3 elements in here. Okay? So I have an element here, another element here, another element there. B inverse A. Don't forget you need to have the order correctly, otherwise you cannot do the multiplication. B inverse A, it would be this thingy times A. And A is negative 140, 113, 113, 214, 214, and 130. What do you think the result of this will be? Three by 3 times 3 by 4. The result will be 3 by 4. It is a 3 by 4 matrix that you do the calculation. Where does it go? Right underneath x1, x2, x3, x4 inside the body of the tableau. What else do you need to do the calculation? B inverse B, which will be this thing times B, original B. All these things are original, coming from the original problem. They don't come the previous iteration. B inverse B, and the B is 10, 20, 15, 10, 20, 15. What would the result of this be? It's a column vector. It's where it goes inside the tableau. Now CBB inverse, one thing else we need to do the calculation. That is CBB inverse A minus C. You need to multiply CB by B inverse by A. You do this as the last type of calculations that you do. Why? Because some of them you do up there. You can either use the B inverse, you can either use the B inverse A from this calculation, whatever it is, or you can do CBB inverse and use them from there and just multiply them by A. So it reduces the specific calculations that you have to do. If you do it with Maple, you can do them all at the same time. Minus C. Where's minus C? The original C. So you do this multiplication, you subtract C from it, and the result will be at that side of the at the Z row of the tableau. Now, what do you think the size of CBB inverse A will be? The same as C. It's the same as C, because we are subtracting this thing. These are matrices and vectors. You can only do this calculation if they are the same size. So what is C? It's 1 by 4. This, when you multiply it, the result will be 1 by 4. Okay? And they go inside the tableau.